We are starting curve sketching today with logarithmic and exponential functions. And some parts of it are a little bit different, or one part of it in particular is different from what we've done in the past. So that's something that you really need to practice over the next several days. Like, to me, this is what you're going to focus on. The rest, building a second derivative chart and finding where the local maxes and mins, that's all the same as it was in the past. It's just the algebra involved in finding the derivatives is different because it's a different function. So, but it's still worthwhile definitely practicing that and making sure that we're really good at that. And by now, we've been doing this for several units with all different kinds of functions. So hopefully you can nail it on this one and we don't have anybody confused about how the charts work, that kind of thing. When you look at the test that was just handed back, there is some good feedback. Like there were some places that people's thinking went wrong. Not just you made a mistake in doing the derivative, but where your thinking went wrong. It's really important that you can determine which of those mistakes you made. Was it a mistake in the process, in the carrying out of the process? You dropped a negative or something like that. Or was it a misunderstanding of what the process tells you or what it does or how you did it, something like that, right? Those are two big differences. So if you're setting yourself some goals right now, that would be a goal to make sure that you understand the full process of the curve sketch and all of that good stuff. And then, like I said, determining the nature of the asymptotes is different for these kinds of functions. And so that's what we're going to spend several days really trying to get the hang of. Okay, so that's something you should be reflecting on and thinking about, am I getting this? Am I not getting this? What am I missing? That sort of thing. So we're going to start just looking at the asymptotes of this first function. We're going to write this down again. I think we wrote this down yesterday. You can tell when we write something down over and over and over again how important I think it is. Not only is it important, yesterday we were talking a lot when we were solving equations, we were talking about it like it's important because I know the domain and range, what the possible input and possible output of the different functions are. We're also going to do, we're going to do this guy as well because we're going to need it eventually. Log x or ln x, same idea. But it's also important that we understand when we examine the nature of the behavior around the asymptotes or where it would have asymptotes, what kind of asymptotes these functions have. And it's going to get a little bit crazy. Like, it's not as straightforward as in previous types of functions where it'll either be this type or this type, and you can kind of narrow it down to the types. Lots of things can happen in these kinds of functions. But the point is, as we're doing it, we need to know what e to the x is doing. So you have to think about the function, think about the curve. As x goes to infinity, what does e to the x do, and so on. That's how we do it. So you really need to be visualizing the graphs and thinking about the graphs. That's part of it. And the other thing is these graphs can do things like, over the course of the next few days, we're going to be doing some sketching, but in some other circumstances, we might not be doing a full sketch, but I would encourage you to use technology to sketch the graphs and get a sense of what's happening. Okay? Because it'll be things like it has an oblique asymptote at one end and not at the other end. It's got a vertical asymptote at the other end. Or it's got an oblique asymptote at one end and a horizontal asymptote at the other end. Or a horizontal asymptote to the left and a different horizontal asymptote to the right. Like, all kinds of different things can happen with these graphs. Okay? So So it's just a little bit different, and it's a bit of a different process how we look at it. Let's take a look at the vertical asymptote of this guy first. The one thing that's the same about this is, when do vertical asymptotes occur? When the denominator is 0. So this is going to be when e to the x minus 2 equals 0. So e to the x equals 2. And again, we're solving equations here, all that stuff that we've been doing. It's a simple equation, but you don't want, if you're writing a test or something and you're under a time crunch, you don't want to be taking a ton of time to do this sort of stuff, because we got to do these little guys over and over and over again. So I think that should work out to x equals a ln of 2. So there's a vertical asymptote at x equals a ln of 2. That makes sense? And then what do we do when we find the vertical asymptote? Like this. Yeah, we want to determine the behavior around it. So we'll do this, the limit as x approaches ln of 2 from the left of the function y. And so I'm going to get out my calculator, and I'm going to figure out what the ln of 2 is. And I wouldn't necessarily write all this down, but I'm going to write it down now. Is about 0.69. So to be just before it, to the left, maybe I use 0.6. And to the right, I can use 0.8, something along those lines. Okay. So I'm going to use 0.6. Minus 2. And I get a negative number. So this is going to negative infinity. And then we're going to do the same. And I got positive, so that one looks like it's going to positive infinity. You could get even closer, and you could see that, like, you might... Exponential and logarithmic functions are a little bit different, because they do grow much quicker often than the other ones that we've looked at. So the values I got, if you didn't check those, I got negative 22 and 17. Not very big. Could a function be at negative 22 and then like turn and go the other direction and actually approach me? Sure, it's possible. Typically not the kind that we would sketch, because that would be tricky to sketch, but yes, it definitely could happen, right? So maybe you want to get even closer and make sure that it is trending upwards or downwards. Try a couple of values. Punching these into your calculator isn't always too hard, and if you could just scroll back and change the number slightly, it might be a value. If I change that to 0.7, I get a much bigger number. I think I got 17 before, now I got almost 300, so I can see that, yeah, it's definitely going up there, right? So do a thorough check. Make sure that you've convinced yourself. For this one, I checked 0.8 and 0.7 just to be sure. But that looks good. That part wasn't too bad. That did probably feel moderately familiar in terms of what we'd done in the past. Because the vertical asymptote occurs when you have a denominator of 0. So now, horizontal asymptote, and what you're going to notice is we're actually going to look for horizontal and oblique asymptotes together. There is no, we used to check it with the degree of the numerator and denominator. That's not going to work here. So we're going to start examining, and this is the process that's a little bit different. We're going to start examining it, and in our examination, we're going to determine what kinds of asymptotes it has and what they are, and then maybe do some testing of behavior after that as well, if we need to. Okay, so here's what we're going to do. When do horizontal asymptotes and oblique asymptotes occur on graphs? Like, where in the graph do we see that happening? This is a good question because it will help you remember. Don't draw this, but okay, so I've got a graph here. Where on the graph do we start to get the behavior around a horizontal asymptote or an oblique asymptote? John, what do you think? It kind of could. Where are you going to be more guaranteed to get it? Yeah. At the ends, the extremes going to the left and the right. In other words, if I'm looking way over here or up here or whatever, I'm going to find something maybe. If I'm looking over here, in the middle, I'm not sure. All kinds of things could happen. Okay, this graph could come like this and do something like that. So it's not in the middle that I worry about. It's way off to the left and way off to the right. So that's what we're going to be doing as our test. We're going to say as x goes to negative infinity. And let me rewrite this, y equals 4 over e to the x minus 2. And here's what we're going to do. This is the tricky part. I'm just going to think, what happens to this when I put a really big negative number into e to the x? Or into the function in general, whatever the function happens to be. And what every graph or every function is a little bit different, but you're going to kind of break it down in your mind into different parts. This part's doing this part's doing this part's doing this, and then put those pieces together to get an overall idea of what the whole thing is doing. Anybody tell me something about what's happening? So this is the exponential function e to the x. So take a look at this graph. What am I looking at here? So you're looking at the blue line, because that's e to the x, which is the one that we're doing. It's not e to the negative x, it's e to the x. And as I put a really big negative number, negative x, like imagine, pick one, negative 100, negative 1,000, negative 1 billion, approaching negative infinity as much as we can. What happens to e to the x? Mason? Approaches zero. Gets really, 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 really small. Okay, so we have 4 over e to the x minus 2. I shouldn't write it here. I'm going to write it somewhere else. I'm going to write it over here. 4 over e. I'm just writing this so that we can talk about it. So this, normally I wouldn't write this down. This gets really small. That's not the technical term. Gets really small. It approaches 0, right? But basically it gets so small that it's irrelevant. And that's what we're talking about, exponential functions. Any function that's approaching 0 will eventually get so small it's irrelevant. But exponential functions grow or shrink so quickly that it very quickly gets irrelevant in the picture. So if I imagine that being gone, what's the rest of the function look like? 4 divided by negative 2. Y equals 4 over 0 minus 2. 4 divided by negative 2, which is negative 2, right? So as x approaches negative infinity, y approaches negative 2. Because it's like 4 over 0 minus 2. So therefore we have a horizontal asymptote at y equals negative 2. That's one direction. Okay. Let's do the other one. As x goes to positive infinity. So again, I have 4 over e to the x minus 2. So as e to the x goes to positive infinity, as x goes to positive infinity, what does e to the x do? Looking at the graph, thinking about the graph, or thinking about what you know about exponential growth. Jason? Gets very large. It approaches infinity. Do you agree with that? Yeah. Okay. So let me just write some of this down. This is just my thinking. Again, you wouldn't have to. So e to the x approaches infinity, which means if this gets really big, e to the x minus 2. If e to the x is going to infinity, what is minus 2 gonna? Is that gonna stop it from going to infinity? I don't think so. So as that's getting really big, this whole thing is getting really big. So what's happening to this whole thing? Gets really small because it's in the denominator. See how you have to think about it on all these different levels? You got to think about the different parts. And it gets even a little bit harder when there's more x's in the equation, which we'll see one of those in a moment. So this whole thing gets really small. So what do you think our conclusion here is? As x approaches positive infinity, what do you think? Y approaches 0. Very good. So this is what I'm saying. Look at this. We had a horizontal asymptote going to the left at negative 2. But we've got a horizontal asymptote to the right at 0. Now we got to do our testing behavior. So I'm going to let, f at x equal y so that I can do this. And in the past, we used values like 100 or maybe even 1,000, negative 100, negative 1,000 to do our testing. You might find those to be way too big, and the numbers on your, like it'll go off your calculator. It'll be too small for your calculator to be able to represent. So we're probably just going to use negative 10 here and figure out what's happening. So I'm going to punch this into my calculator. 4 divided by e to the negative 10 minus 2. So I got negative 2.0000045. That's also a nice way of confirming that I have the right asymptote, right? Remember, that's the same as before. That, okay, yeah. And this only works for horizontal asymptotes, but for horizontal asymptote, it does work where it's very close to negative 2, and you could check negative 11 and see that it's even closer, I suppose, if you really wanted to. But so I think I've got the right horizontal asymptote. What does that tell me? What else does it tell me? Approaching from below, because it's just a little bit more negative. Just a little bit below. And when we're curve sketching, that's what's important. And again, I can just scroll into my equation here and delete the negative and check positive 10 equals, and I get approximately 0.00018. I feel like I've said this so many times, but you really, really, really need to know the difference between the vertical asymptote tests and the horizontal and oblique asymptote tests, how to do them, how to read them, what you're doing, because it's not a matter of whether these are positive or negative. That's not what we care about. What we care about is its relationship to the asymptote, right? So this is negative, but that's because the asymptote's negative. Like make sure, like, and I saw people making those mistakes on the last test, so make sure, not the last test, the last test, but make sure you're thinking through that you understand the difference between, we don't care whether this is negative or positive. That's not what's important here. Any questions about any of this? What do you think about it? Anything else we need to do here? I think we're good. All right, let's try another one. What do you notice about this question? Do we notice anything about it? Yeah, so it's almost the same as the last one, which is nice. So we can just say, note the vertical asymptotes are the same, just so we don't have to worry about it. We're not going to redo that part. So let's take a look at the horizontal and or oblique. I know that some of you are going to want to just kind of, or maybe not even try, but you just will memorize the different types. Oh, this looks like the one we did in the lesson that was like this, so it's probably going to work out like this. I mean, if you can't help it sometimes, but be careful relying on that, because they are all very different. And again, the point of this is that not just you can recognize 3 or 4 different types that happen to come up in class or in the homework, but that we can go through the process and build a picture of what's happening for any kind of function, right? So over the next few days, you're going to have to find time to go through the thinking process, doing this yourself. Again, it might look easy watching somebody else do it, who's done it a bunch of times and who knows what's coming and all that stuff, and who points out the thinking. And you go, oh yeah, that makes sense to me. Hearing somebody else saying something and it making sense to you is very different from generating that thought yourself. And that's what you have to practice, generating those thoughts yourself from scratch, which is what we're going to do, right? Over the next 3 days, we're going to spend a lot of time on this. As x goes to negative infinity, what happens? Same kind of thing. So this time it's 4x over 0 minus 2. So what is that? That e to the x part that was in it, this part right here, when x goes to negative infinity, that part's going to 0. So I can kind of sub a 0 in my head and think about that as not being important. So what does the rest of it look like? The top's getting really large. What kind of large? Negative large, though. Yep. But not small as in approaching 0 small. Like, we want to be careful about what kind of small we're talking about. Yep, very good. So I knew what you meant. Negative large. It's a big negative large. Okay, and what about the bottom? Anybody have any thoughts here? Yeah, that's true. What do you think the oblique asymptote might be? If you had to guess. What kind of 2x? Negative 2x, does that make sense? So 4x divided by negative 2. So y approaches negative 2x. So it's an oblique asymptote. Because the e to the x it's not going to be exactly negative 2x, because the e to the x will still have a value. It'll never actually be 0. Is it going to end up being just above or just below? I don't know. We'll check that. But it's going to look something like negative 2x. As x goes to negative infinity, 4x over negative 2 will look like negative 2x. It'll be very similar to that straight line. There's no reason, like it's not approaching a horizontal asymptote or something like that. It's just approaching negative 2x. Does that make sense? So, therefore, we have an oblique asymptote of y equals negative 2x as x goes to positive infinity. Geez, again, this part's really tricky. What does y approach? Well, it's going to be 4x over infinity minus 2. Once again, this is a whole new kind of thinking that we've never really probably done before, not in the context of a math class like this, at least. It's not clear. When it approaches 0, that part just goes away. You can kind of like ignore it and worry about what's left. Like we just did. 4x over negative 2 is negative 2x. We can just worry about that. What can we do in this case? We can't ignore the infinity. What do you think?
Would it just like go to 0? It's like even though 4x will be infinity is a lot bigger.
Yeah. Who's the bully in this situation, right? Like 4x is going to get, like I'm multiplying by 4. I'm taking a big number and I'm multiplying it by 4. Or I'm taking a big number and I'm raising e to that as an exponent. Like just think about the graph. One would look like this, and one's going to look something like this. And look how quickly that's going to get bigger. And it's going to be so much bigger that it's going to basically take over the entire function. So you're exactly right. Very good. This will approach 0. So in this process, you have to look at the different parts. I'm looking at the different parts that are related to x. Okay? So I'm looking at the 4x and imagining what it's doing. And it's on top. It's getting bigger, but the bottom is getting more bigger, more quickly. So it's going to take over the whole function. And this is going to approach 0. So we've got an oblique asymptote going off to the left, but then we have a horizontal asymptote going off to the right. Very curious. There's a whole thing in mathematics called big O notation. I don't remember a little bit about it from university, but it's kind of along these lines of like talking about which part of the function takes over and determines the nature of the overall function, especially maybe at its endpoints, that kind of thing. It's sort of similar to this kind of thing. Anyway, okay, so now we want to do our testing. So let f at x equal y. I'm going to do the horizontal asymptote first. So I'm going to check 10. So this one's a little bit different because I got 2 x's. So I'm going to do a little trick on my calculator with the a's. I'm going to do 4a divided by e to the a minus 2. And then I'm going to put negative 10 in for a. Scroll up, hit equals. Oh, no, I wanted to do positive 10 first. Sorry, I lied to you. And I get 0.0018. Like, look how small that is already just at 10. What would happen if I put 100 in? Yeah, I put in 100, and I get a scientific notation answer. You might be able to tell if it's positive or negative, depending on your calculator, but I prefer not to bother with that, so that's why I would go with 10. Okay, good. So what does that tell us? Mason? It's approaching 0? Very nice. Therefore, above. It confirmed. We already kind of thought it was approaching 0. Confirmed that, I think. But also we know from above or from below, which if we're sketching, if all you're asked to do is determine the nature of the asymptotes, then that's all we need. But if we're sketching, then we need to know, so we can draw our sketch. All right, negative 10. I got 20.0005. Huh. What happened there? So for the oblique asymptote, if I did y when x equals negative 10, I'd get negative 2 times negative 10, which is positive 20. So I'm very close to my oblique asymptote. In the past, when we were working with oblique asymptotes, we could determine the equation of the asymptote and the remainder part, what was left. Do you remember doing that, the remainder part? And we could sub into the remainder part and just see if it was adding or subtracting above and below. We can't do that here. We don't know the remainder part. We know the oblique asymptote from inspection. We don't know the remainder part. In this case, I can just kind of, it's negative 2x, it's easy to do. So I kind of know that, it's going to be positive 20. So I'm just above here. The oblique asymptote would be 20. The function is 20 and a tiny bit. So I'm above. If the oblique asymptote was more complex, you might need to actually sub in and check them both. You know what I'm saying? Okay, so that process might be a bit messier. But nevertheless, that's how we do it. We do actually sub into both the oblique asymptote and the actual function and look at the difference between those two values. Any questions about that? It's a bit different, right? It's a bit new. It's not as step, step, step. In the past, when we did the sketching, curve sketching, there was a process. You could follow these steps of doing the long division and getting the remainder part or whatever it was. That's not necessarily happening here. Okay. We only have 20 minutes left. Oh my goodness. I think this was going to be our first one. We were going to do a second one. I think I want to skip to the second one because I want to do one with a lawn in it. So I don't know if we're going to have time for both. Let's start with this one. There's one little trick when you have a lawn or a log or something like that. It would be, now you start to see why it might be, or once we get into this, why it might be a little bit trickier if it was log of some other base or e, or an exponent with a base not e, and you have those extra lawns kicking around as constants when you're doing your derivatives. You're going to see how that would mess things up a little bit more. First thing I want to always remind myself with lawn, back up to the very top of the note, the graph, what does it look like? In particular, the domain is that it doesn't exist for 0 or negatives. So if I tried, look at this is ln x minus ln of x all squared. So if I put 0 in, then it's not going to work. As a side note, what if this was like ln x minus x squared? Because putting 0 in would work for that, but it wouldn't work for that. So if it doesn't work for any part, it doesn't work for the whole thing. Just to throw that out there. Okay, that's definitely true the way domains work. We saw that very briefly in MHF, but barely, and it was a long time ago, so you probably don't really remember. So if it doesn't work for any part of the function, the whole function is going to break down, right? But in this case, if you sub it in, all of it kind of falls apart. So 0 or negatives are no good. And why is that important? Because as I'm going through it, if I get those values as critical values or points of inflection or something like that, like where the second derivative is equal to 0, I don't have to worry about it because the function doesn't exist there. Okay. All right. So y-intercept. We're going to do intercepts first. When we're doing a sketch, the instructions for this were sketch. I think we kind of skipped over that. But yi. So that's when you sub in 0. We kind of just talked about this, but we're going to show it anyway. Right? That gives us an error, no solution. When I sub 0 in for x to find the y-intercept, it's not going to work. What about the x-intercepts? That's where I sub 0 in for y and start solving. You might not notice that this is like a minus a squared. So what can I do? Yeah, factor out my a, right, which is actually ln x. So I get 1 minus ln x, I think. So I get ln x equals 0, and I get ln x equals 1. Be very careful about being too quick to say when something isn't true. Again, this is like, I think, where people do get mixed up. This is like x equals e to the 0, which is 1. And this is like x equals e to the 1, which is e. So it's got two x-intercepts at 1 and at e. Okay, so now we're going to go into asymptotes. What do you think about vertical asymptotes for this one? When do vertical asymptotes occur? When the denominator is 0. We certainly don't have that. But what else do you think about this situation? It can't go negative. And it's not going to be 0. Why? Remember a couple of days ago when we, or maybe it was yesterday and the day before, I can't remember, when we talked about these and we wrote out the asymptotes. This has a vertical asymptote of x equals 0. Right? Like that function itself has a vertical asymptote in it by the nature of that, its individual function. Its nature has one. So it's not about the denominator, it's about this has an asymptote. So, go back and find our work here. I think we should be testing to see what's happening. Is there an asymptote? What's happening there? So we're going to, and I think we can suspect there is an asymptote. We're going to check what's happening around it. Okay, so vertical asymptote, x equals 0. Kind of with a question mark because we're just going to test and see limit as x approaches 0 from the right. We don't need to do the left because we know it doesn't exist in the left. Again, like this is a bit more of a holistic process. We're using our understanding of the graph to think about, well, it doesn't exist in the negative, so I'm not going to worry about that. But every one of these functions is going to be a little bit different. The ln ones tend to work out that way. Okay, of y. And so I punch in something really close to 0, punch it into my calculator, and I'm going to get, whoops, I don't get 0, sorry, that's not true at all. I get negative infinity. So I have a vertical asymptote, and as I approach from the right, it's going to negative infinity. Again, I think you want to check a couple of values. So check a couple of values very close, to maybe even 2 or 3. If you can punch it quickly into your calculator, 0.01, 0.001, that might be getting too big, but check some values that are close, might be worthwhile. So we do have a vertical asymptote at x equals 0. Okay, what about horizontal asymptotes or oblique asymptotes? As x goes to negative infinity, wait, this graph doesn't do that. That's what we were just talking about. So we don't have to worry about that part. It doesn't go off to as it goes to the left, it goes to negative infinity with that asymptote at 0. So that's it. Okay, so we just need to check what's happening here. So ln of 10 minus ln of 10 all squared, ln of 20 minus ln of 20 all squared. Minus bracket ln 100 bracket all squared. What do you think? I got -5, I got -2, -5, or -3, -6, -16. They're not approaching anything weird. It's just going off to negative infinity. I could put in some bigger numbers, again, checking a few. So therefore, there's no horizontal or oblique asymptote in this case. There is no trend. There's nothing interesting happening. It's just like a ln function would. So again, we're using our idea, like our understanding of a ln function of the basic one. It often does this. Maybe that's what this one does too. I'm going to do, before I start that, I'm just going to do both derivatives. So y is ln x minus ln x all squared. So y prime, derivative of ln x, 1 over x, ln x all squared, so I bring the 2 over, times the ln of x to the 1 now, times the derivative of what's inside, which is 1 over x. So this is 1 minus 2 ln x over x. And the second derivative starts to get a little bit nasty because I have to do quotient rule now. So the derivative of the top, the 1 is just a constant, so that's gone. So I get -2 times 1 over x, and then times the bottom. Minus the top times the derivative of the bottom, which is just 1. All over the bottom squared, and I'm just going to clean this up a little bit. I notice something nice happens here. So if I had all those extra little constants of like ln of 2 or ln of 3 or ln of 10 because I had a different base, it would get messy. This is why it's nice to be able to use this number e in this process. Is everybody okay so far? Okay, so let's take a look at critical values. This is where y prime does not exist or equals 0. So y prime does not exist when x is 0, but the whole function doesn't exist when x is 0, right? I'm looking right here. So this does have a denominator, but I don't need to worry about that because, so you might state it just for yourself to remind yourself to always be checking. Okay, y prime does not exist when x equals 0, but the function doesn't either, so I don't really need to worry about it. So let's figure out where y prime equals 0. 1 minus 2 ln x equals 0. That's where the numerator of the derivative equals 0. So this is where ln x equals 1/2. And x equals e to the 1/2, which is a square root of e, which I believe is about 1.6 root e, whoops. Yeah, 1.6. Just for my reference for later, I just want to know about where that is. We okay here? Okay, and POI is where y prime does not exist or equals 0. And again, it does not exist when x equals 0. But, because it's x squared on the bottom now, but we've already talked about that. So I'm thinking about it, but it turns out it's not relevant. So I've got this -3 plus 2 ln x equals 0. The numerator of the second derivative. I know I'm going kind of quick here, but I want to make sure we get all of this in. And that's where ln of x equals 3/2, positive 3/2. So x equals e to the 3/2. And that works out to about 4.5, I believe. First derivative equals 0, critical values, that's local max, local min. Like, you should be thinking about this, reminding yourself constantly, that's what that is. Previously, at one point, we did a first derivative chart to find those locations and determine is it increasing or decreasing before and after that whole thing. And we did a first derivative chart yesterday just because it's still a good thing to do. But now we're doing the second derivative chart to look for points of inflection as well. So we're looking for concavity, right? So let's go ahead and do that. And so this is just the second derivative. So when x is, we start at, like, where does the function start? It starts at 0 or as approaching 0. So from 0 less than x less than e to the 3/2. We only have this one. And then e to the 3/2. And then when x is greater than e to the 3/2. That's the square root of e cubed, right? Okay, so I am going to put the second derivative into my calculator. There it is. So I've got bracket -3 plus 2 ln a bracket divided by a squared. And I'm going to put something, and I got an error because, hopefully that doesn't mess up the memory on my calculator because of whatever a was before. I had -10 or something in there, right? So it gave me an error. That makes sense. Now I got to put something in this interval here from 0 to 3, e to the 3/2, which is 4.5, so I can pick 1. Oh, it did. It messed up my memory, so I got to type the whole thing in again. All right. -3, bracket. -3 plus 2 ln a, bracket, divided by a squared equals, I got -3, so I got negative. So this is concave down. Here it's 0. And now I put something else in, so I'm going to put 10 in. And I get a positive. So this is concave up. So this is a POI. And now I got to go find where that is. And I can do exact value stuff here because e to the 3 over 2, like I can punch that into my calculator nicely. All right, so original function, ln of a minus bracket ln of a all squared. So I'm going to put in, let's see, this is e to the 3 over 2, shift E, store that in A, and I got negative 0.75, so negative 3 over 4. And I've got one critical point, and it's in this place here, so it's 1.6, which is going to be in this interval. So I've got a local max, because it's concave down, so that's going to be a maximum in that interval. And that's at the square root of e, or e to the 1/2. And so now I can put that in. Oh my goodness. E to the 0.5, store that in A, reevaluate, and I got 0.25, so I got a quarter. So I got these nice, perfect answers. Oh, and I got tons of space here to do my sketch. This is great. But I only have 2 minutes. I got lots of space. I don't have any time left. Okay, so this is going to be, I'm going to call this point A. I'm going to call this point B. And I've got my 2 intercepts. Don't forget those. And I've got a vertical asymptote. So I've got an intercept at 1 and an intercept at E. E is 2.6, 2.7 in that area, right? So I've got 1.6 E, and then way over here somewhere I'm going to have my POI. So I'm approaching, and I go through 1, and I hit a max, and then I go down, and then somewhere here it turns. This is x equals 0. This is point A, I think I called it. This is point B, that's a POI. And this is 1, and this is E. And see how it goes. Remember, we checked this. That makes sense now. It goes off to negative infinity. There's no asymptote going off in that direction.